Download this code from codegive.com, link in the description below. OK, let's dive into a comprehensive tutorial on using antlr4 for parser generation, specifically focusing on the concepts often covered in Eecs4302 or similar courses, and building upon the foundation typically laid in the first 5 parts. This part 6 will concentrate on semantic actions and attribute grammars to compute values and perform type checking within your parser. Eecs4302 and antlr4, Context and Overview. Eecs4302, or a similar compiler construction/programming languages course, often uses antlr4 as a practical tool to implement parsers. The course generally covers lexical analysis, scanning, breaking the input text into tokens. Syntax analysis, parsing, building a parse tree based on a grammar. Semantic analysis, checking the meaning and consistency of the parsed code, example type checking, variable declaration. Intermediate code generation, optional, translating the code into a machine-independent representation. Code optimization, optional, improving the generated code. Code generation, optional, creating machine code. antlr4 excels at lexical and syntax analysis. Part 6 will focus on techniques to embed semantic analysis directly into your grammar file using semantic actions and by constructing an attribute grammar. This allows you to validate your parsed input and compute values during the parsing process. Part 6, Semantic Actions and Attribute Grammars with antlr4. 1. What are semantic actions and attribute grammars? Semantic actions. These are snippets of code, typically Java in antlr4, that are embedded directly within your grammar rules. They are executed when the corresponding rule is successfully matched during parsing. Semantic actions allow you to store information from the parse tree. Compute values based on the parsed input. Perform error checking, example type errors, undeclared variables. Build an abstract syntax tree, AST, if desired, though antlr4's parse tree is often sufficient. Attribute grammars. An attribute grammar augments a context-free grammar, CFG, with attributes that hold semantic information associated with grammar symbols, terminals and non-terminals. Rules specify how these attributes are computed and propagated through the parse tree. Synthesized attributes. Computed up the parse tree. The value of a synthesized attribute at a node is determined by the values of attributes of its children. Inherited attributes. Passed down the parse tree. The value of an inherited attribute at a node is determined by the values of attributes of its parent or siblings. 2. Benefits of using semantic actions and attribute grammars. Tight integration. Semantic analysis is integrated directly into the parsing process. Increased efficiency. Semantic checks can be performed as the parse tree is being built, rather than in a separate pass. Improved error reporting. Errors can be detected and reported more accurately and contextually. Clarity. In some cases, embedding semantic actions makes the grammar more readable and understandable. 3. Example, a simple calculator with type checking. Let's build a calculator that supports integer and floating point numbers, addition, subtraction, multiplication, and division, and performs basic type checking to prevent operations between incompatible types. 3.1. Grammar, calculator.g4. 3.2. Explanation of the grammar. At header. This section includes Java imports. Here, we import java.utility hashmap to create a symbol table. At members. This section declares Java member variables within the generated parser class. We declare a symbol table to store the types of variables. *xpair returns double value, string type. This is the key part. We define the xpair rule with return attributes, value, of type double, and type, of type string. This means that when the xpair rule is successfully matched, it will return a double value, the calculated result, and a string representing the type of the expression, int, float, or error. Similar returns clauses are in term and factor. Semantic actions within the rules * the code enclosed in curly braces are semantic actions. Let's break down some of them. *stat, xpair new line system.out.println, $xpair.value, after parsing an expression, the semantic action prints the calculated value, the value attribute, of the xpair rule to the console. *stat, id equals xpair new line. This rule handles variable assignments. *string id name equals $id.text, gets the text of the id token, the variable name. *string xpair type equals $xpair.type, gets the type attribute returned by the xpair rule, the type of the expression being assigned. *symbol table.put, id name, xpair type, stores the variable's name and type in the symbol table. *xpair, xpair op equals plus dash, term. This rule handles addition and subtraction. The semantic action. * retrieves the types of the left-hand side, $xpair.type, and the right-hand side, $term.type. * performs type checking. * if both operands are integers, performs integer addition/subtraction and sets the result type to int. * if either operand is a float, performs floating point addition/subtraction, casting integers to floats if necessary, and sets the result type to float. * if the types are incompatible, example strings, prints an error message and sets the result type to error. You could extend this to handle other types or custom error conditions. * sets the value attribute to the result of the operation. * factor, id. This rule handles variable references. * retrieves the variable name. * checks if the variable is declared in the symbol table. * if declared, retrieves the variable's type from the symbol table and sets the type attribute accordingly. * if not declared, prints an error message and sets the type to error. *lexirules defines how to recognize identifiers, integers, floating point numbers, new lines, and witty space. 3.3. Generating the parser. 1. Save the grammar * save the code above as calculator.g4. 2. Use antlr4 * from the command line, in the same directory as calculator.g4, run. This will generate the lexical, parser, and listener/visitor classes. 3. Create a main class * create a Java class, example main.java, to run the parser. 4. Compile and run * compile and run the main.java class. 3.4. Expected output. The output shows the type of x is correctly inferred as int. The type of y is correctly inferred as float. The expression x plus y is evaluated to 12.5, the float version. An error message is printed because z is used without being declared. 4. Key concepts illustrated. Return attributes the returns double value, string type clause allows you to define attributes that are passed back from a grammar rule. This is essential for synthesized attributes. $rule.attribute notation within semantic actions, you use the $rule.attribute notation to access the attributes of other rules. For example, $xpair.value gets the value attribute of the xpair rule. $token.text notation you use $token.text to access the text of a token. For example, $id.text gets the text of the ID token, the variable name. You can also use $token.type to get the token type, example the numeric ID of the token. Symbol table the symbol table, a hash map, is used to store the types of variables. This is a common technique in semantic analysis to keep track of variable declarations. Type checking the grammar performs basic type checking to prevent operations between incompatible types. If a type error is detected, an error message is printed. 5. Enhancements and further exploration. Error handling implement more robust error handling using antlr4's error listeners. You can customize the error messages and locations. More complex types extend the calculator to support other data types, such as booleans or strings. You'll need to update the type checking logic accordingly. Functions add support for function declarations and calls. This will require a more sophisticated symbol table to store function signatures, parameter types and return types. Inherited attributes the example above mainly uses synthesized attributes. To illustrate inherited attributes, imagine you want to ensure that all variables within a particular block are declared before use. You could pass down an inherited attribute representing the set of declared variables in that block. Abstract syntax tree, AST. While antlr4's parse tree is often sufficient, you might want to build a custom AST. You can do this by creating AST node classes and using semantic actions to create and link these nodes during parsing. The AST provides a cleaner representation for further processing. Visitors/listeners while this example primarily uses embedded actions, consider using antlr4's visitor or listener pattern for more complex semantic analysis. These patterns can separate the parsing logic from the semantic actions, making your code more modular and maintainable. The visitor pattern, in particular, is well suited for traversing the parse tree and performing computations or type checks. 6. Example, using a listener, alternative approach. This demonstrates a simplified approach using a listener. It provides an alternative to in-grammar semantic actions for some tasks. This example creates a listener to track the declaration of variables and report errors if an undeclared variable is used. And here's how to modify main.java to use the listener. Key changes for the listener approach 1. Calculator listener implementation implements calculator base listener. You override the enter and exit methods for specific grammar rules to perform actions when the parser enters or exits those rules. 2. Parse tree property this is a utility class provided by antlr4 to associate arbitrary data with nodes in the parse tree. Here, we use parse tree property string to store the data type of each expression. 3. Parse tree walker this class is used to traverse the parse tree. The walk method takes a parse tree listener and the parse tree as input and calls the appropriate enter and exit methods as it walks the tree. Explanation of the listener approach The enter ID method checks for undeclared variables when the parser enters an ID rule. The exit stat method is executed when the parser exits a statement. This is where we store the variable's type, if it's an assignment statement, and print the expression's type. Exit xpair, exit term, and exit factor determine the type of expressions. Benefits of the listener approach Asterisk separation of concerns. Asterisk the semantic analysis logic is separated from the grammar, making the grammar cleaner and easier to read. Asterisk more modular. Asterisk you can easily add or remove listeners without modifying the grammar. Asterisk more flexible. Asterisk listeners allow you to perform complex semantic analysis that might be difficult to express directly in the grammar. Disadvantages of the listener approach. Asterisk requires additional code. Asterisk you need to write separate listener classes. Asterisk can be less efficient. Asterisk listeners might involve multiple traversals of the parse tree, which can be less efficient than embedding semantic actions directly in the grammar. 7. Choosing between semantic actions and listeners/visitors. Asterisk semantic actions. Asterisk good for simple tasks that can be easily expressed within the grammar rules. Asterisk can be more efficient for certain types of semantic analysis. Asterisk can make the grammar more complex and harder to read if overused. Asterisk listeners/visitors. Asterisk good for complex semantic analysis that requires multiple traversals of the parse tree. Asterisk promotes separation of concerns and modularity. Asterisk can be less efficient than semantic actions. In general, for simple tasks like type checking, variable declaration tracking, and basic calculations, semantic actions can be a good choice. For more complex tasks, especially those involving multiple passes over the parse tree or complex data structures, listeners or visitors are often a better option. Good luck. Let me know if you have further questions.